Hello everyone. Today I will be discussing about VLSI practical. So in this part B, that is preparing layouts. So the aim of this experiment is to simulate CMOS inverter. The objective is to prepare layout of CMOS inverter with and without capacitor, simulate and observe voltage transfer characteristics. Equipment or software required are PC with microwind 3.1 or higher version, any version installed. So since this is the most basic one which you all might be knowing, the logic diagram of this. So we need a P channel MOSFET and an N channel MOSFET, for which gates are connected together to give a common input, and here source and drain of which are connected together to take the common output. Here is the VDD supply and this is the ground. The operation of this you all might be knowing, that when we give the input as logic 0, since it works as input inverter, here the P channel MOSFET will switch on, acts as a closed switch for logic 0, and this acts as open switch, so there is no connection towards the ground. So this VDD through which the current flows and the output will be 1. Similarly, when the input is logic 1, then the P channel MOSFET is off, open switch, and N channel MOSFET is on, so there is a low resistance part towards the ground, so output will be 0. So this is the symbol and this is the input output relation, and the operation which I have just explained. When the input is 1, PMOS is in the pull up is off and NMOS is on, hence output is logic 0. When input is 0, PMOS in the pull up is on, NMOS is off, hence output is logic 1. So this is the ideal voltage transfer characteristics which we have seen in the theory lectures also. So from which we can classify into 5 regions. This is region 1, 2, 3, 4 and 5. So in the different regions, different operation, NMOS off, PMOS linear and so on. If I connect across at the output load capacitor, then we can see the charging and discharging of the load capacitor as and when the output changes from logic 0 to logic 1 and logic 1 to logic 0. So if I connect a load capacitor, the energy delivered from the power supply is CVDD square, and an energy stored in the capacitor is half CVDD square. So when the output switches from 0 to 1, since we all know the PMOS transistor turns off, NMOS is on, discharging the capacitor. In the other way, when it switches from 1 to 0, the capacitor will charge. So the energy stored in the capacitor is dissipated in the NMOS transistor. No energy is drawn from the supply during this transition. So this is the sample or expected stick diagram or layout of CMOS inverter. So here the pull up is the P channel MOSFET, this is the gate, and this is drain and source. Here we have the gate, so gate common line I have drawn so that to give gate, and here is the source and here is the drain. And similarly the drain and source are to be connected together to give a common, to take the common output Y. So this is the stick diagram on layout, for which this is the simulation waveform what you can observe. When the input is 1, output is logic 0. When the input is logic 0, output is logic 1. So such waveform you can observe, and you can also observe the voltage transfer characteristics. So the transition actually should happen exactly at the VDD by 2. If there is a mismatch in the sizing of the MOSFETs, as I explained in the theory lectures also, then this at the middle which the transition should happen may not occur. So it may drift. So we need to see the sizing of the MOSFETs also appropriately. So this is the theoretical part. So now I will show you with the tool how to make the stick diagram and layout using the microwind software. So I hope you all can see the icon here, microwind 3.8. So I'll just open this. We'll minimize this one. Okay. Now you can see here on this window, you can see the palette of layers. There are so many number of materials which are shown here, like N-well, N plus diffusion, P plus diffusion, contact, metal 1, metal 2. So many metals are there. In each different layers you can use all these different metals. And you can see here the VDD supply and the ground. You can, if you want to give a single pulse, you can give single pulse. You can give the input as a sinusoidal input. You can give the sinusoidal input. You can give a continuous pulse, which is called as a clock. You can give a clock. And if the contact is between P plus diffusion and metal, you can use this directly. If it is between metal 1 and metal 2, you can use this. If it is N plus diffusion and metal 1 contact, then you can use. Similarly, you can explore so many things. Here you can see the virtual capacitance which you can attach. And if you want to observe the output waveform using the visible node, which is shown here, you can observe the output waveform. So now I'll quickly show you how to draw and how to check the DRC, that is the design rule checking on this to satisfy all our conditions. So first in the pull-up, what we need? P plus diffusion. So I draw a P plus diffusion here. Okay. Now in the pull down, I need N channel MOSFET. So I draw a N plus diffusion. Okay. Now to make the gate, I need to have polysilicon. Okay. So I take the polysilicon. I am drawing a single line so that I can give a common gate input. Now I use the metal one to take the output. Okay. If you want to do the extensions, you can do it like this. Just click here. Now I want to give the supply through metal lines. You need to give the supply voltages through the metal lines. So this is VDD and this is ground. Click here and place here. That's it. Clicking and placing. Now I will make use of contact here. I can use N plus diffusion and metal one also. Here I have, see, N plus diffusion and metal contact. I can place here. And the same again I can place here, N plus diffusion and contact. See, this is P plus diffusion and contact. And there is one more P plus diffusion and contact VD. Now contacts are established. What about, see, the background or the black area what you see here is the P substrate. And the spacing between the two dots is what you can see here as the lambda. So if I have 1 lambda as 2 nanometer, then how much nanometer is needed, that you can calculate. So here we are using CMOS 14 nanometer, 8 metal copper materials are used, and even you can use FinFET also. Now I want to give the since the background is P substrate, I want the N substrate for P channel MOSFET. So I will place a N-well here to overcome the P substrate and to act as a N substrate, and but this also has to be polarized. Polarizing means giving the supply as VDD. Now I want to give the input. So I give the input here anywhere on this, and I name this as A. Let me say input as A. Okay. Say assign, and I take the visible node and place it here and name it as output Y. Say assign. Now you can see my layout or stick diagram is complete, but I need to check the design rules with the help of the DRC design rule checker. So no design rule error, congratulations. Have you seen this? So this should come up so that my design rules are satisfied. Now go to simulation and run simulation. Okay. Sorry. Here I have selected FinFET. I need to select the foundry. Select the foundry as, let me say, I am selecting CMOS 06 rule and say OK. And now run. Oh my god. Select foundry. If you see here, when the input is 1, output is coming out to be 0. So this you can observe, and if we come across voltage versus voltage here, can you observe? This is the voltage transfer characteristics. So my input voltage is 0 to 0.8, output voltage is also 0 to 0.8, and my transition is almost occurring nearby 0.4, which is VDD by 2. So you need to take the screenshot of this one, save it and send it along with the file. Voltage versus time as well, voltage versus voltage. Okay. So this is the way you are supposed to perform the experiments of any logic design which is given to you. You need to prepare the stick diagrams, first check the DRC and then simulate and verify your design. So you can notice here that it also shows the power dissipation for this CMOS what we have designed is 0.817 microwatt. Getting? So this also can be noticed. I hope you have understood. If you want to look at the 3D picture of the stick diagram or layout what you have prepared, click on this 3D. You can see here the 3D picture. Getting everyone, this is how it will be done when we fabricate on chip. Okay. Say close.